welcome to Mathematics Gymnasium once again, and this is your German mathematics teacher. Like I said in the last class, or in one of the previous videos, and will continue to maintain that mathematical concepts are interrelated, and as such, the curriculum developers made effort to arrange them in sequential order in such a manner to engender transfer of learning experiences. Unfortunately, we, or most of us, the curriculum implementers, do not emphasize this, thereby making it difficult for learners to get the best, to the extent that some actually demonize mathematics, and by extension to some of us. But like I have always maintained, that on this page or channel, depending on where you are watching from, most of the things that your teacher did not tell you that are very important to your mathematical literacy, you will hear from here. Now, we are going to discuss logarithms today, laws of logarithms. I understand that the topic I'm going to discuss takes some sort of algebraic dimension. However, I'll be careful enough to ensure that you are not demoralized, because I understand that so many persons have phobia for letters when it comes to mathematics. But that is taken care of, so just pay attention. Let x, y, and z be real numbers greater than 1, as in 2, 3, and 8, such that z is equal to x raised to power y, implies 8 is equal to 2 raised to power 3. Then the logarithm of z to base x is equal to y. It implies a logarithm of 8 to base 2 is equal to 3. This is the definition of logarithm, and this is the application for clarity. So I can safely put here definition. So just before you were thinking that the definition in mathematics would be like that of economics or in geography, no. This is how we define stuff, with illustrations in mathematics. In other words, whenever it's possible for you to present a number in index form to a particular base, as in 8, that could be presented as 2 to the power of 3, then the logarithm of that number, 8, to the base or base 2, is equal to 3, the power to which 2 must be raised to give us 8 when expressed in index form. So this is the definition of logarithm, and it is very important because after all said and done, when it comes to the solution of problems involving logarithms without table, most of the time you are likely going to arrive at the logarithm of a number to a given base. Then, if the instruction is for you to evaluate a particular logarithm, this is what you will refer to the definition, and that is what will take you to the final solution. So now I'll solve an example with respect to the application of this definition. Example 1. You may be told to evaluate log 81 to base 3. This is how far the question may be presented. Then what do? You now go ahead to say it implies, or you say given log 81 to base 3, let log 81 to base 3 be equal to whatever letter you like, say x. You now say if a raised to the power b is equal to c, it implies that log c to base a is equal to b. And you state definition. I am mentioning this because this is called application in the taxonomy of measuring cognitive objective of education in mathematics. Cognitive objective is the aspect of education that deals with the ability to read, write, and solve written problems or solve academic problems. So this is one of, and there are 6 stages in measuring that, and it's called the taxonomy of measuring objective. That's why mathematics specifically is marked step by step. I've explained that in one of the previous videos. So having stated this, you will get your mark for application. Now this is analysis. You are analyzing. So you now say, having established this definition, it now suggests to you that 3 raised to the power x is equal to 81. Another person may prefer to leave 81 here and take this 3 to raise to the power 8. It's the same thing. Now, if you have interacted well enough with indices, you will understand that 3 raised to the power x, if 81 is to be expressed in powers of 3, it will be equal to 3 raised to the power 4. So you have now expressed 81 in powers of 3. So it implies that 3 raised to the power x is equal to 3 raised to the power 4. Therefore, x is equal to 4. Hence, don't forget we were told to evaluate log 81 to base 3. Log 81 to base 3 is equal to 4. This is the answer. Now you observe that this was not presented as an equation. We'll get that when we start discussion on algebra proper. It was presented as an expression. An expression is a mathematical statement that does not contain either equality or inequality sign. So this was presented, or is presented, as an expression. But from there you created an equation by yourself. And that's one of the reasons I say mathematics is very democratic. Whatever you say, let it be. We speak similar to God's language in mathematics. Let it be. It will be. The examiner will see agree to it to be when you say let it be. For instance, here I said let log 81 to base 3 be equal to x, and it has been. Okay? Now that takes care of this. Having established that, I am going to link the laws of logarithm to the laws of indices then I will list the rest. Now, for everything I do, when it comes to the explanation or discussion of mathematical concepts, I take my time to explain to detail. That is what I owe anyone who I have to explain anything to, and that is what every other teacher does owe any student. Now, let x raised to power y be equal to p. We know what it's going to be, or it implies that log p to base x is equal to y. By definition, we are trying to establish a link between the laws of indices and the laws of logarithm. Already we have established a link between the definition of logarithm and the presentation of a term in index form, or a number proper per se in index form. Similarly, and x raised to power z be equal to q. So it implies that log q to base x is equal to z. Right? Now, if we want to multiply p and q, it implies that p times q in this form is going to be x raised to power y times x raised to power z, and that will be equal to x raised to power y plus z, by reason of law of indices, that when two index numbers are multiplying each other, we simply retain the base and add the powers. Don't forget that y is log p to base x, z is log q to base x. So it now means p times q, it implies that p times q is equal to this. Now, if we now want to take the logarithm of p times q, it will mean that this now becomes the power, isn't it? It will now mean that the logarithm of this to base x, log to base x of p times q, right? So, and that gives us log p to base x plus log q to base x. That takes us to the first law of indices, law of logarithm. So we can now equate this to this. It implies that log p to base x plus log q to base x is equal to log to base x of p times q. So this is the first or addition law, and it is taken from the multiplication law of indices. Now, the reverse could still be, the converse could still be obtained. If we decide to divide, say we put division here. Okay, I think I should pause it here and take the division. After the second one, then I'll just make mention of the other law, the law of indices that translates to the law of logarithms. So this is the addition law. So log p to base x plus log q to base x is equal to log to base x of p times q. Okay. I think I should illustrate it numerically. Log 8 to base 2 plus log 4 to base 2 equals log to base 2 of 8 times 4, and that will be equal to log to base 2 of 32. Now, I decided to do it like this because I have not explained another law that would have made it easier for us to arrive at this being equal to 5 immediately. So, we now make reference to the definition that we did before. We now have a single logarithm to a base 2, log 32 to base 2. Don't forget, I made mention that when it is all said and done, you will arrive at a single logarithmic expression to a given base. From there, you make reference to the definition to arrive at your final answer. Now, at this point, we'll now say let log 32 to base 2 be equal to, say, x. 32 now will be equal to 2 raised to power x. We know that 32 is equal to 2 raised to power 5. We now say it implies 2 raised to power 5 is equal to 2 raised to power x. Therefore, x is equal to 5. So, if you were told to evaluate or simplify, that's because it involved two logarithmic terms. If you were told to simplify log 8 to base 2 plus log 4 to base 2 on this side alone, you would have done it this way by the application of this law. When you simplify it, it takes you to log 32 to base 2. Then you now refer back to the definition that log 32 to base 2 be x, or whatever letter you prefer to use. It implies that 32 is equal to 2 raised to power x. 32 can be expressed as 2 raised to power 5. Therefore, x is equal to 5. You now come to the conclusion that log 8 to base 2 plus log 4 to base 2 is equal to 5. And like I said, this is 3 and this is 2, because log 8 to base 2 is 3. Log 4 to base 2 is 2. So 3 plus 2 will give us 5. So you can see the simulation between logarithm and indices. Okay, right about now, I am just going to do the converse. In other words, the reverse side. X raised to power y equals p implies that log p to base x is equal to y. X raised to power z equals q implies log q to base x equals z. So if you want to divide p by q, it follows that p divided by q implies x raised to power y divided by x raised to power z, which implies x raised to power y minus z. Don't forget that y is equal to log p to base x and z is log q to base x. So p divided by q, p divided by q can still be presented as p over q, will now be equal to log p to base x minus log q to base x, because if we take the logarithm from here, this p it now becomes log p divided by q to base x is equal to log p to base x minus log q to base x. So this is the subtraction law of logarithm derived from the division law of indices. You can see that they are interrelated. Now that is why it's important for one to learn concepts that are interrelated and emphasis be made by the teacher, so that it will be brought to the consciousness of the learner. And learner also has a duty to attempting to applying them and also to ask questions when there is any confusion. So I have taken care of the definition, the addition law of logarithm that was derived from the multiplication law of indices, and the subtraction law of logarithm that was derived from the division law of indices. The division law of indices gave rise to the subtraction law of logarithm. Now, I'll just make mention of each of the law that is related to the other laws that I am going to list. That is because it's important to understand the origin, and I have done that by establishing the relationship between logarithm and indices. So every other thing can easily be detected by anyone who intends to become independent. And that's one thing I encourage people to try to be when it comes to learning of mathematics. If you strive to be independent, at the point you become, you begin to discover things by yourself. And when you, at that point, you will now get to the limelight and realize that the myth that people who are very good at mathematics usually have their brain work somehow is not true. Instead, people who are good at mathematics reason in a manner that would make it difficult for people to sell fake things that are not correct to them, because they will use their logical reasoning technique to counter whatever argument the person is bringing. Recording from law of indices that x raised to power 0 is equal to 1. So by definition, log 1 to base x is equal to 0. So whatever the base is, if it is the logarithm of 1 to any base. That is because it means that the base can only be raised to 0 to give us 1. So this is another law of logarithm. The next one, x raised to the power 1 is equal to x. If we apply the definition also, it implies that the log of x to base, the log of this x to base x is equal to 1. This is another law of logarithm. Now, of course, these are direct translation from indices, but for the understanding of the definition of logarithm and the presentation of index numbers, one may think that they are two far apart concepts, but they are indeed very closely related concepts. Now look at this. Here's another law. Log x raised to the power n to base y is equal to n log x to base y. Now, we still have another, this 1, 2, 3 plus the previous 2, making 5 so far. Then, the other one, okay, log x base x, log x to base x raised to the power n, that is derived from here, is equal to n, and that is because, now let's see, if this is n x to base x and this one goes to the back, which means it's going to be n log x to base x. Don't forget that from here, log x to base x is equal to 1. So it will be as good as n times 1. Therefore, log x to the power of n to base x is equal to n. Now, it's important to understand that most of these laws, of course, have their roots. When I say root, I mean their origin in indices. And like I tell whoever cares to listen, it is not important to cram any of them. The only important thing that is advisable is to interact with them, apply them, and every time the need arises for you to apply them, state them. That is how you internalize them, rather than trying to cram them. Now, it's in the consistency with which you work with problems related to their applications that you internalize them to the point that you can easily recognize where such